Hello, everybody. Today we're going to talk about lesson 4.8 on sine and cosine in the same right triangle. So in particular, we're going to explore a relationship that happens with complementary angles, that is, angles that add up to 90 degrees, and how that relates to sine and cosine in a single triangle. Okay, but in order to do that, we're going to need to be able to solve for missing sides in a right triangle. So we're going to start with a little bit of that. If you want to join this activity and try some of this yourself, feel free to do so. I am going to play both roles here. I'm going to show you a bit of what would happen for either of the players, since this might have been something you did with groups in class. So let me hop over here, and I'm going to solve for some missing sides in these triangles. Just real quick recap. When you are finding a missing side, there's kind of some basic steps that I always tell people to follow. First, you figure out where the hypotenuse is and label the opposite and adjacent sides based on one particular focus angle in the triangle. Once you've done that, you pick whichever ratio makes sense for the sides that are in the problem. Like if you're looking for a side, that's important. If you already know a side, that's the other important one. And then you set up an equation and solve. Okay, cross multiply and solve. You know what, that's just talking. Why don't I do it? Okay, so here's a triangle. I've got 41 degrees here as an angle that I know, and I'm interested in finding the value of x, and I know that this side is 7. Well, follow my own advice. First thing I should do is label this side as the hypotenuse, and because it's across from the right angle. And then in terms of this 41 degree angle, I would say that this side over yonder is the opposite side, and this side down here is the adjacent side. So step 1, complete, did my labeling. Now, as far as what's relevant for the problem, I think that would be the 7 and the x. Those are the two important sides, the thing I know and the thing that I want to know. And so I'm thinking, which trig ratio uses adjacent and hypotenuse? Oh, it's cosine. Cosine uses adjacent and hypotenuse. So when I set up an equation to solve this, I will write cosine of what? Cosine of my angle 41 degrees is equal to, let's see here, it's adjacent side on top, right, for cosine, CAH, adjacent over hypotenuse. So it would actually have to be 7 over x. Well, that's different. That's okay, we'll be fine. And then because now I've got this equation, I want to solve it, I'm going to change this into a fraction by putting it over 1, and then I'll cross multiply to solve. So x times cosine of 41 doesn't really do anything. And frankly, neither does 1 times 7. 1 times 7 is still 7. Then to get x by itself, we need to divide both sides by cosine of 41. And at this point, I need to get out a calculator because I don't know what cosine of 41 is. And I certainly don't know what 7 divided by cosine of 41 is. So calculator, what is 7 divided by cosine of 41? 9.275? Sure, why not? So about 9.3, give or take. Yeah, neat. So x equals about 9.3. That was a nice little problem, wasn't it? All right, round two. Here's another triangle. Now this time we've got, it's 7 again. Mysterious. And x, and this angle is 49 degrees. Again, I need to start by doing my labeling. The side is the hypotenuse. X is the hypotenuse, that is, because it's across from the right angle. And then as far as the other sides are concerned, I would say that 7 is opposite from 49 degrees. And this side down here is adjacent to 49 degrees. So which trig ratio is right this time? Well, we have the opposite side and we have the hypotenuse. So which trig ratio uses opposite and hypotenuse? O and H? Well, that's sine. That's sine. Sine's the winner this time. So we'll set up a problem involving sine, S-I-N, sine of 49, right? It's always in terms of the angle measurement when you set up one of those trig ratios. And we know that sine is opposite divided by hypotenuse. So once again, I'm going to be looking at 7 divided by x. A little bit of deja vu here. Okay, so put a 1 underneath, and then I can cross multiply to solve. 1 times 7, x times sine of 49. X times sine of 49 is equal to 7. And just like the problem on the previous page, I'm going to finish by dividing. I'll divide both sides to get x by itself. I want to cancel out sine of 49. So if I do this division, what will it be? What will it be? He wonders aloud. Those go away. And x is equal to, drum roll please, 7 divided by sine of 49. 9.3 again. No, crazy. Wait, what's going on here? That's the same number. That's the same number. And the numbers, wait a minute here. Wait, look at this triangle. Look at this triangle here. What's the deal with that? Are these the same triangle? Are these the same triangle? Did we just solve for x in the same triangle 2 times? We did. We did. And why is that? I'm going to jump ahead to this page right here so you can see both of those triangles side by side. And what I want you to notice is that if there's a 90-degree angle here, then that only leaves 90 degrees for the other 2 angles in the triangle. And so that means that 49 and 41 have to be the 2 angles in these triangles, because that's what adds up to 90 degrees, right? And so, yeah, it was the same triangle both times. That doesn't really explain entirely why cosine of 49 and cosine of 41 and sine of 49 were the same value. But here's how I think about that. If you consider that triangle again with me, and you think about 49 degrees and its opposite side. Its opposite side is 7. All right, and the hypotenuse is x, okay? And then again, when we look at this other angle, 41 degrees, if we think about opposite and adjacent hypotenuse, well, for that angle, this is the adjacent side, but the hypotenuse has not changed now, has it? So as far as setting up 2 equations go, when we set up those 2 equations, we're really using the same numbers everywhere, because the opposite of 49 is the same as the adjacent of 41. So for that reason, it turns out that sine of 49 is equal to cosine of 41. Crazy, because opposite and hypotenuse are switched for those 2 angles. Sorry, I said that wrong. Because the opposite and the adjacent sides are switched for those 2 angles, but the hypotenuse remains the same. Now, this is just one specific example of it. How do I know this is going to work all the time? Might be a reasonable follow-up question. And for that, I'm gonna hop over to the activity again and skip a few pages. And here is the general version. The sine of any acute angle is equal to the cosine of the complementary angle. I agree. I do absolutely. That's what we were just talking about, that if you have sine of one particular angle, I don't know, I'll represent it with the letter x. So that's going to be equal to the cosine of another angle that would make x add up to 90. So x plus 90 minus x equals 90. That's a weird thing to say. Our example made more sense, didn't it? Like sine of 49 was equal to cosine of 41, because those 2 numbers together make 90. Can I prove that this works in general? I can, and you can too. Explain why using this sketch. So over here we have theta as the stand-in for our angle measurement. If I were to find the sine of theta as it suggests up here, then that would represent the opposite side, y, divided by the hypotenuse, h. So sine of theta is equal to y over h. But then when I start thinking about the other angle, this angle 90 minus theta, that would have an adjacent side, 80j of y, and still the hypotenuse is h. And so cosine of 90 minus theta is equal to the same thing. It's equal to y divided by h, because the opposite side of one angle is the adjacent side of the other angle within a single right triangle. Neat, I think. Where does this work in practice? Well, we saw this on the table before, right? Like with the 25 degrees and 65 degrees, those angles add up to 90. And we saw previously that the first two values when we were using the table would just swap. The sine and the cosine of those two complementary angles are equal. Or I should say the sine of 25 is equal to the cosine of 65 and vice versa. So just a little bit of practice to ramp down for today. So if I know that sine of 55 is equal to cosine of some other number, I know that that number needs to be 35 because 55 and 35 makes 90. Likewise, if sine of y equals cosine of 28, I know that this will be true if I find the other number that with 28 would make 90 degrees. So it's 62. This one is weird. This one doesn't have any numbers at all. But based on what we talked about a minute ago, how did I get that 62? Well, I did the 62 by taking 90 minus 28, yes? And to get the 35 in my mind, I did 90 minus 55. And so for this last one, if I want to find the measurement of W, it would be equal to 90 minus Z. Wacky, but true. All right, hopefully that is useful for somebody, but feel free to track down your math teacher if you want to hear more about any of this.